problem. And Hilbert's sixth problem is about the axiomatic derivation of the laws of physics, mainly justifying the laws of statistical physics starting from the laws of dynamics. So as we all know, over here, statistical laws govern macroscopic quantities like temperature, pressure, fluid velocity. And those laws of statistical physics are usually time irreversible. For example, think of the second law of thermodynamics. On the other hand, the laws of dynamics are, so they usually govern the microscopic quantities like the trajectory of a particle, the orbit of your microscopic system. And these are usually reversible in time. Here we think of Newton's laws, we think of Hamilton's laws, think, for example, of Schrödinger equation if you're doing quantum mechanics. So this passage from the reversible to the irreversible comes as a result of several averaging and limiting operations. And these operations are what creates an arrow of time in your laws of statistical laws. And so the Hilbert's sixth problem is mainly asking to give a rigorous justification of this passage from the microscopic to the macroscopic. And this will constitute the main problematic for us as well today. So let us start by dealing with a classical example of this passage. So this is Boltzmann's kinetic theory. So in this case, the passage from the microscopic to the macroscopic happens through an intermediate scale that's called the mesoscopic scale. And this scale is where the Boltzmann kinetic theory comes to play. So let us start with, I'll give a very quick review of this theory. So what the setup or the physical setup is that suppose you start with a system of n particles. Each of those particles has a radius r, and those particles are undergoing elastic collisions, okay? So what Boltzmann theory tries to answer the following question. Can we derive an effective equation for the one particle density function? So this is, for example, you can think of it as the probability of finding a particle at position x moving at velocity v at time t. Without, of course, we'd like to have an effective equation for that without having to solve for all the trajectories of all the particles in your system. Think of this n to be a huge number. So it's really rather ineffective and unimportant to solve for all the particle trajectories. So what you do is that you start with the n particle distribution function. So this is, I will call it f sub n. So it tells you the position, the probability, if you like, of finding a particle of particle 1 at position x1, velocity v1, up to particle n at position xn and velocity vn. And this thing solves the classical Liouville equation. So this is, again, a large system of transport PDEs. And this is, in a way, equivalent to Newton's equation. So you didn't make the passage here to the mesoscopic scale at this level. And you can also talk about the one particle distribution function in this case, which is obtained from this f sub n by integrating over the last n minus 1 particles. So you do integration over x1, x2, v2, all the way to xn vn. And what we'd like to find is that we essentially would like to find an effective equation for this f1 of t at x1, v1. And this is where the celebrated Boltzmann equation appears. So this Boltzmann equation is supposed to provide a good approximation for this one particle distribution function in the limit when n is very large. So Boltzmann's equation, as you probably all know, so this takes the following form. It's dt plus v dot grad x. So there's a transport term here applied to the distribution function. And this is equal to the collision operator, which is a nonlinearity. It's a bilinear nonlinearity Q of f. We won't go into, I won't even write what this collision kernel is, because it's not something that we will be focusing on today. So the mathematical question here is to give a justification of this approximation. And this was a big challenge. And in several aspects, it is still a big challenge in terms of getting a good approximation. But this was mainly resolved in 1975 by Landford, who proved, and here I mentioned several later works that clarified and extended Landford's work. So what Landfords theorem tells you that the Boltzmann equation indeed appears an effective equation for f1 of txv in the limit when the number of particles goes to infinity and the radius of each particle goes to 0. Now, those two things cannot go to infinity in a free way, and R cannot go to 0 in a free way. They have to go to 0 according to something called the Boltzmann grad scaling law. So this happens when n goes to infinity and R goes to 0 in such a way such that n times R to the d minus 1 is order of 1. Okay, so this is called the Boltzmann scaling law, and this is the only scaling law for which we have a justification of Boltzmann's equation as an effective equation for the one particle density F1. Okay, so if you want more precisely, this F1 of t x1v converges in a certain sense to the solution of the Boltzmann equation, f of t xv, as n goes to infinity and R goes to 0 along the above scaling law, along this scaling law. So this is was a big success for the kinetic framework, and this kinetic framework proved to be highly informative for practical and for theoretical reasons, and was extended to many other particle systems. We have several kinetic equations for particle systems in addition to Boltzmann's equation that hold in different regimes. So what we'll be trying to do today is we'll be trying to answer Hilbert's sixth problem for wave systems, if you like. So we'll try to justify the theories of non-equilibrium statistical physics for waves, starting from first principles. So having realized that waves are as fundamental objects, physical objects, as particles, 20th century physicists tried to draw a parallel of the theory of statistical mechanics for nonlinear wave systems. Okay, so at the level of the non-equilibrium statistical physics, this was started by Peierls in 1929, Hasselmann in 1962. So Peierls was deriving equations for phonons, if I'm not mistaken. Hasselmann was derived corresponding kinetic equations for water waves, and then the theory was extended and generalized by Zaher and many others, starting from the 60s. So here, compared to the particle system, the microscopic dynamics is given by like a Hamiltonian PDE, for example, a nonlinear dispersive PDE. Okay, so this will be our microscopic system, which it will be a nonlinear dispersive PDE. This will be our first principle that we'll be starting from. Okay, so for us today, we will take this nonlinear dispersive PDE to be the nonlinear Schrodinger equation, which is given over here. So it is IDT plus Laplacian applied to V is equal to some nonlinearity, which we take to be V squared V, the cubic nonlinearity. I will comment on the sign of the nonlinearity, could be plus, could be minus. I will comment on that in a couple of slides. Okay, and so the initial data is V naught. And the usual setup for this theory is that you take the physical space to be a torus of size L. So which means we're talking about a box of size L, if you like, a cube of size L with periodic boundary conditions. So there's one extra degree of freedom, if you like, here, that this box we can take different aspect ratios of its side lengths. So what we will we'll take our TD sub L, our torus, to be the L times the box 0 gamma 1 cross 0 gamma 2 cross 0 gamma D. So the usual case of the square torus happens when gamma 1 equals gamma 2 equals gamma D equals 1, which is something that we will also cover by our results. So we say, however, there's some analytical difference in the results, depending on whether those gamma 1 up to gamma sub D, the aspect ratios of the torus, are rationally dependent or rationally independent. So we say that they are rationally independent if k dot gamma is different from 0 whenever k is an integer vector. So here I should point out there's a qualification that k is an integer vector. So k is in ZD. Okay. So if you take a vector k in ZD, you take its dot with gamma 1 up to gamma sub D. If this is always different from 0 whenever k is not 0, we say that the gamma 1 up to gamma sub D are rationally independent. And we also talk about being generically irrational if we have some Diophantine condition on the gammas. I won't go too much into that today, but basically you should think of A rational torus is, think of the case when gamma 1 equals gamma 2 equals gamma d equals 1. Irrational torus when the aspect ratios are allowed to be very irrational numbers. And this will make a difference in terms of the resonances of the equation. Okay, so we'll comment, as we said, on the sign of the nonlinearity a little bit later. All right, so let's talk about the parameters of the problem. Okay, so previously when we were talking about the Boltzmann theory, we had mainly two parameters, the number of particles and the radius of each particle, n and r. So here we have sort of similar parameters. But before we get into that, so let's remind ourselves that the aim is to get an understanding of the long-time behavior of solutions or of ensembles of solutions for the nonlinear Schrodinger equation. You could, by all means, try to answer this question deterministically, which would be sort of similar to trying to solve for the particle trajectories in an unparticle system. However, this is as before, and even it's much more complicated now than before. So this is hard to answer because of a rich set of possible long-time dynamics and behaviors that are exhibited by the nonlinear Schrodinger equation. So you have some periodic in time behavior, have quasi-periodic behavior, have soliton type behavior. And so this is even talking, starting with the considering the NLS equation on the torus on a compact domain. Even if you start with the NLS on RD, for which there is a analogous theory to the one that I will be discussing today, even there, the asymptotic behavior might be well understood. But this is, so for example, you might have that all solutions or finite energy solutions scatter. However, the intermediate type of time behavior, the intermediate time behavior of large solutions is not very well understood. We don't know what happens to the solution between the initial data and its scattering state. And this is really where the kinetic equation, this is the time scales where the kinetic equation is interested in. Okay, so just as in the case of an unparticle system, we abandon the hope of trying to solve for all solutions in a deterministic way. So instead, we take the statistical approach and we ask whether we can describe the behavior of generic solutions or behavior of ensembles of solutions. So going back to the parameters of the problem, so we already encountered one parameter of the problem, which was the size of the torus over here. Okay, so we're talking about, and this size of the torus over here will be in a way, if one wants to really push forward this analogy with the Boltzmann theory, this would be comparable to the number of particles in the Boltzmann theory. Okay, so in addition to L, we have another important parameter is the characteristic size of the solution. So for this, to emphasize the characteristic size of solution, which we will be calling lambda, we'll take the ansatz, we'll write V equals to lambda U, and think of U as having size 1 in L2 norm. The L2 norm is a conserved quantity for this equation, so there's no loss of generality over here. And if you look at the solution of the V equation, it is essentially the same as the U equation, but you get a factor of lambda squared in the nonlinearity. So here over here as well, I rescaled space so that I'm always working on the square torus, on the usual torus of size L with periodic boundary condition, but this comes at the expense of introducing those beta 1 factors in front of the Laplacian terms. So I have beta 1 d by dx1 squared up to beta sub d d by dx d squared. So beta 1 would be something like 1 over gamma 1 squared, and beta 2 1 over gamma 2 squared. So in particular, if you're working, if you only want to think about the square torus today, all the betas are equal to 1. Okay. So what is the kinetic description here for this equation? So in order to introduce the kinetic description, let me introduce now a dependent parameter. So it's a parameter that is defined in terms of the lambda, which is, I remind you, is the characteristic size of the solutions, and L, which is the characteristic size of the domain. So I define alpha to be lambda squared or times L to the minus D. And this, the reason why we introduce this is that this will be the characteristic size of the nonlinearity. Why so? I'll give you a heuristic justification of why this is the characteristic size of the nonlinearity. We will be considering generic solutions or generic functions in L2 of 2D that have size 1 in L2. Remember, we're looking at U that has characteristic size 1 in L2, and we'll take a sort of a random L2 function that has size 1 in L2. And I look at the size of the nonlinearity, lambda squared U squared. Okay. So if you pick a random L2 function that is normalized of size 1, there is no reason for this L2 function to have a particular spike at a certain point. So its L infinity norm would have size order of L to the minus d over 2. So it had a sort of a uniform L infinity norm. For it to have a size 1 L2 norm on a domain that has volume L to the d, then its L infinity norm has to be of order L to the minus d over 2. Of course, this is a heuristic that needs to be justified, but for now, we're just presenting the physical theory. So let's carry on with this heuristic. So if I look now at the size of the nonlinearity over here, I get lambda squared. I put one copy of U in L2, which has size 1. I put two copies of U in L infinity. Okay, so I get L infinity squared, and I get that this has size lambda squared L to the minus d, which is what I defined to be alpha. So alpha will be the characteristic size of the nonlinearity. Okay, now the kinetic conjecture is the following. It says that in the limit as L goes to infinity and alpha going to 0, so this is the large box limit, sometimes it's called also thermodynamic limit, and the limit as alpha goes to 0 is called the weak nonlinearity limit. This is part of the reason why this theory is sometimes called weak turbulence theory as well. The effective, what we'll be looking for are effective dynamics of the expected value of U hat of tk squared. Okay, so what we do is that we take the Fourier transform at time t of my NLS solution. So U as my NLS solution, I take its Fourier transform in space. When I take its Fourier transform in space, since I'm working on a torus of size L, the Fourier transform lives on a lattice of spacing 1 over L. So the K over here, and for the rest of the talk, will be in ZD sub L. So this is 1 over L ZD. Okay, basically it's the lattice of spacing 1 over L. And what I will be after is the expected value of the modulus square of the Fourier nodes. This is the quantity that we will be seeking an effective equation for. Okay, this equation so this quantity is definitely related to the sort of the space covariance of the field, but let's not get into that over here. So the expectation or the conjecture is that this quantity is to be approximated by a solution of a kinetic equation, which would be the analog of the Boltzmann equation. And this kinetic equation is called the wave kinetic equation, and it's written over here. So let's try to read through this equation. So what we will be trying to say is that this quantity is approximated by n of tk. Okay. Actually, I'm lying a little bit over here, so you need to change this little t a little bit, but we'll talk about that on the next slide. Okay, so where n of tk satisfies the following equation. dt of n of tc or k is an integral over c1, c2, and c3, such that c1 minus c2 plus c3 is equal to c. Okay.
Excuse me, the expectation is with respect to what?
The what?
The expectation. It's
the expectation. Again, this is something that I will clarify on the next slide. So usually, typically, what you'd like it to be is that the expectation with respect to some distribution of initial data.
okay.
Okay. I'll make everything here a little bit more mathematically precise on the next slide. Okay. After we present this equation. Yeah. Thank you. Okay, so what we were reading this equation, and what we were doing is that we said that we're integrating over c1, c2, c3, such that c1 minus c2 plus c3 is equal to c. So you have this integrand. So in this integrand, I used the shorthand notation. I denoted n1 to be n at c1, basically, and in general, nj is n at time t evaluated at cj. So you have this integrand. And another important thing, or probably the most important thing in this equation, is that the integration also is happening over a delta function for which we are imposing that c1 squared minus c2 squared plus c3 squared minus c squared is equal to 0. Okay, so this is, it's not exactly c squared, it's c squared sort of modulated by the betas, because you remember when I rescaled the x's, I had in the Laplacian, I had over here, this is my definition of the Laplacian. So this appears over here by, in terms of, instead of talking about c squared, I need to change c squared a little bit. So as a first reading, I would suggest to think of beta as equal to 1, and then these are just the absolute value of c1 squared and absolute value of c squared, c2 squared, etc. Okay, so let us make precise all this. In what sense does this kinetic equation approximate the modulus squared of the Fourier transform solution of NLS? And this will be written over here. So more precisely, what is expected is that for times close to something called the kinetic time scale, which is 1 over alpha squared. So alpha is was the size of the nonlinearity. So 1 over alpha squared is 1 of the size of the nonlinearity squared, which in terms of the original parameters L and lambda, this is L to the 2D over lambda to the 4. What we expect is that we expect that the average of u hat of tk squared is approximated by the solution of the wave kinetic equation evaluated at time t over t kinetic at frequency k, at wave number k, if you like. And this approximation should hold in the limit when L is very large and alpha is very small. So this statement over here, I will be calling it, this is, calling this statement for rest of the talk approximation or approx statement. Okay, and n of tc is a solution of the wave kinetic equation with initial data n initial. I take the solution of the wave kinetic equation with initial data n initial, and u of t is a solution of NLS with initial data u initial. Okay, so for this thing to make sense, it has to, for this thing to hold, it has to hold at time t equals to 0, which brings us exactly to the question, what do we mean by this averaging operator? So we want this to hold at time t equals to 0, which means that I will take a distribution of initial data for NLS for which this thing makes sense. We call such distributions well-prepared data. So what the data we take for our NLS equation is the following. So I need to specify the initial data for NLS. So equivalently, I can specify the Fourier transform of this initial data. And this Fourier transform is the following. I take the initial data for the kinetic equation, n initial. I take square root of that because n initial, I forget to mention that, n initial is greater than or equal to 0. And if it is, then n of tc remains non-negative. So I take square root of n initial at k, and then I multiply that by some independent random variables, eta k of omega. So eta k is a collection of mean zero random variables that satisfy the expected value of eta k squared is equal to 1. Okay, so in other words, the effect of this is that if I look at the expected value of u initial at k, then this would be equal to n initial at k, because the expected value of the random variables eta sub k of omega, I took it to be eta sub k squared, I took it to be 1. Okay, so in other words, this thing over here, I need to have it to hold at time t equals to 0. And this is what we mean by well-prepared data. So hopefully this explains what is meant by this expectation over here. So the expectation over here will be an expectation with respect to the distribution of the initial data over here. Okay, so in practice for our theorems that I will be stating later on, those eta k will be IID. We'll take them to be IID random variables, independent. So they are independent and identically distributed for different k's. And we will take them to be either Gaussians, for example, eta k could be jk of omega, or they can be uniformly distributed on the circle z equals 1. So in other words, this would be a random what we do in this second case is effectively what is called the random phase approximation, which is what we do is that we take a deterministic modulus for the Fourier transform, but we randomize the phases. Okay, so that's what we you should think about this well-prepared data. We're taking initial data that has a deterministic modulus, and this deterministic modulus is given exactly by the initial data for the wave kinetic equation, but we randomize the phases, okay, for each k in a identical and independently distributed way. All right. So, any questions before I continue? All right. So this is what the conjecture is. This is what the physical theory tells us that what should be holding in a way. And so then we move on to the question is, so the main question that we'll be interested in for the rest of this talk, how can we make this? How can we prove this? Okay, this is right now a sort of a well-formulated mathematical question. I'm starting with initial data as such for the nonlinear Schrodinger equation. So at time t equals to 0, I have this approximation, if you like, to be holding. I'm taking initial data for NLS that are distributed in the same way as given to me by the initial data for the wave kinetic equation. Now the question is, at later times, does this approximation hold? Okay, and as we said, this approximation is supposed to hold in the limit when the size of the domain goes to infinity and the size of the nonlinearity is very small. Okay. All right, so before we go on to talking about some mathematical results, let us make some remarks about this equation. So this is the wave analog of Boltzmann's equation, and there are, of course, here we started with our microscopic system to be the nonlinear Schrodinger equation. In general, you can start with a different microscopic system, like, for example, you can take Hasselmann's equation for water waves or many other dispersive systems or nonlinear wave systems of interest, and you would get different versions of this wave kinetic equation. And there are inhomogeneous versions of this. So what I have just discussed are, I took initial data that sort of gives you a homogeneous version of this equation. The inhomogeneous version of this equation is exactly the same, except that you have a transport term similar to the one that you see in the Boltzmann equation. So the Boltzmann equation, remember, there was dTv plus v dot grad, dTf plus v dot grad f. So you can also have here c dot grad x in n, and n would be also depending on both space and c. Okay, so this would be called the inhomogeneous version of this wave kinetic equation. And this is highly informative in applications, including oceanography, nonlinear optics, crystals, and even in the field of condensed matter. This is also something that is used very much in order, for example, there are physics papers that use this kinetic equation to understand the dynamical formation of a Bose-Einstein condensate, and even after the formation of a Bose-Einstein condensate, you might want to derive the effect, the kinetic equation around this condensate, which is also something that has been done by several physicists like Newell and Zaher and many others. So this is something that is sort of used all over nonlinear wave theory, and more importantly, or one of the reasons why it's used all over nonlinear wave theory, is that it leads to a framework for turbulence for nonlinear waves. And so I won't go too much into this because that's a subject on its own. But what I would like to say is that this framework of turbulence gives conclusions that are very similar to those that are given in hydrodynamic turbulence. For example, you get power law spectra out of this equation as, if you like, as stationary solutions of this equation. And this was investigated as well from a mathematical point of view by some works over here that I cite here. So the main mathematical question that we will be interested in is to provide a rigorous derivation of this equation, starting from the nonlinear wave model, which is NLS, and basically in precise terms is justifying this. This is what we mean by the rigorous justification or the rigorous derivation of this equation. Okay. And this rigorous derivation is not only a question of interest in mathematical physics, but it's also something that can help understanding the exact regimes of limitations of this theory of wave turbulence, which is something that is poorly understood for some models. So now I get to the remark that I promised you about the sign of the nonlinearity. So it turns out that the sign of the nonlinearity plays a little role in this theory. And the reason for that is because of the weak nonlinearity assumption, alpha much less than 1 that we're taking. Okay, indeed, if you look at the potential, the nonlinear energy or the potential energy of the NLS equation that we're talking about, so this in the regime of solutions that we're talking about, this potential energy or the nonlinear energy is approximately has size alpha times the kinetic energy. Okay, so maybe I can write something down over here. So the Hamiltonian or the energy of NLS is given as follows. So the energy of U is equal to 1/2 grad U squared dx plus 1/4 or lambda squared over 4, if you like, the integral of U to the 4 dx over TD sub L, TD sub L. Okay, so this thing over here, this is what I'm referring to as the kinetic energy, and this is the linear energy of the equation. This is the nonlinear energy of the equation. So in the type of solutions that we're talking about, this nonlinear energy has size alpha times the kinetic energy, where alpha is much smaller than 1, and as a result, whether this is a plus or minus turns out to have less effect on the theory. An important thing to note is that the kinetic energy itself is something that diverges in the limit that we're taking. So we're talking about solutions that in the limit as L goes to infinity, their total energy goes to infinity, which is something that one always does in what do in statistical mechanics. So this is what you do in the thermodynamic limit. The total energy of the system has to diverge in the thermodynamic. Okay, so here are the remarks. Any questions for now? Sorry, again, I cannot see anyone, but so feel free to interrupt whenever you like. Okay, so we'll be interested in the rigorous derivation or the justification or the rigorous justification of this approx identity that we talked about before. And there were several partial results on this derivation. So for example, for this equation or variance thereof, there's work by Fau, there's work by Daimov and Kupsin and many others. However, the first attempt to tackle the full problem was done in a joint work that we did with Tristan Buckmaster, Pierre Germain, and Jalal Shatta about a couple of years ago. And in this case, we considered NLS on a generic irrational torus. So over there, for technical reasons, we had to consider the equation, the case when the torus was not quite a square torus, but sort of has the relative sizes of the sides of the torus are sort of irrational numbers and generic irrational numbers. We'll talk about where this thing appears in the proof later on. So we considered NLS on a generic irrational torus in dimension greater than or equal to 3, and we were able to prove that this approximation between the kinetic equation and the solution of the Schrodinger equation holds for very large times, T star, that depend on alpha and L. However, the main drawback is that this T star still did not reach the kinetic time scale. So in some sense, we proved that the some minuscule changes to the solution of the Schrodinger equation is dictated by the kinetic equation, but not order of 1 changes in magnitude. Okay. And the major component of this work is resolving completely all the number theoretic issues that appear for this problem. We'll see that a major part of this proof is to resolve a number theoretic problem, surprisingly enough. And so this is where we resolve this. We'll talk hopefully about it later on. Okay, and the main challenge after this theorem is the question, whether we can justify this approximation for times that are closer and closer to the kinetic time scale. Okay, so the holy grail would be to be able to say that this approximation holds for times that are multiples of the kinetic time scale. That's what one would like to do. Okay, so here's the main theorem that I will be discussing today. So this was a joint work with Yu Deng from the University of Southern California. And we adopt a different approach to the problem, which allows us to see, to get much closer to the kinetic time scale and also see some interesting behavior that is happening. Okay, so the statement of the theorem is as follows. We consider the nonlinear Schrodinger equation on a torus of dimension d greater than or equal to 2. And here beta is arbitrary. You could take beta to be equal to 1 as well. In this case, all the beta to be equal to 1. So you're working on the standard square torus. And assume that your initial data for the kinetic equation is a Schwartz function. And you take the initial data for NLS to be well prepared, which means that its modulus is given by the initial data for the kinetic equation, and it's the modulus of the Fourier transform is given by the initial data for the kinetic equation, and the angles of the Fourier transform are randomized, okay, either by Gaussians or by random phase. Okay, and suppose epsilon is arbitrarily large. Then something interesting happens in this case. So remember when we talked about the derivation of the Boltzmann equation, we said that this derivation held in the Boltzmann grad limit. When n goes to infinity and r goes to 0 in such a way such that n times r to the d minus 1 remains order of 1. Okay, so we observe something similar happening over here for the wave kinetic equation, which is something new. Okay, so we see that surprisingly enough, we have two favorable scaling laws in this case that we observe. We notice that if alpha, so remember the analog of L here in our problem is, the analog of n in our problem is L, capital L, and the analog of R is alpha. So we notice that if alpha approaches 0 like L to the minus epsilon, or L to the minus 1 minus epsilon, so these are the two scaling laws, then we can justify the approximation between NLS and the kinetic equation up to timescales that are arbitrarily close to the kinetic timescale within epsilon loss. So it's something like the kinetic timescale times L to the minus epsilon, and epsilon can be arbitrarily small. Okay, so we call those two things favorable scaling laws. However, for other scaling laws, if you don't assume that alpha approaches 0 like this or like this, okay, then for other scaling laws, we notice some divergences. Okay, so for other scaling laws, we notice that the approximation holds for shorter times, t less than t star, and these times are, I'll depict them in the following diagram. So the following diagram really contains the statement of the whole theorem. So let's talk about it. Okay, so on the vertical axis, I take the time in the logarithmic scale. So this is log t over log L. And on the horizontal axis, I take log alpha inverse over log L. So basically, each point on the x-axis corresponds to a scaling law. If you specify a point on the x-axis or a vertical line, this corresponds to specifying a way in which alpha goes to 0. What way does alpha go to 0 when L goes to infinity? Okay, so what the time scale that you would like to achieve is the kinetic time scale. So this is the red line over here. This is the line that we'd like to get to. We'd like to prove the approximation all the way up to this time, up to this that is given by the red line. So our theorem, as I told you, that there are 2 points where we can touch this line. These are the 2 favorable scaling laws that were mentioned in part A of the theorem. And for the other scaling laws, we cannot reach the kinetic time scale. We can reach something that is shorter than the kinetic time scale over here. So this is the blue region in this diagram. Okay. I should point out over here is that if you're working on the rational torus, your theorem stops here, and this is a sharp theorem. You cannot do anything better. If you're working on a generic torus, then this is a bigger region that you can access. Okay, which is it's clarified over here. Another thing, okay, so here there's a typo that I meant to fix, but I did not fix. It says t minus 1 instead of t. Okay, so
sorry,
what
may I ask a naive question, very naive actually. So
yeah, go ahead.
The presence of this epsilon, so could I think of that as being some subleading scale like log or something like that? Or, well, so I'm trying to figure it out. What is the analog of the Boltzmann, you know, constraint, right? So you said there is a precision up to the precision epsilon, you get to the right spot, so to say.
Right, right.
But is this because there is something hidden there, or?
No, this is just saying that this is sort of result. So this is an epsilon, if you want, it's an epsilon drawback of this theorem that you would basically, the reason for that is that we cannot really reach the kinetic time scale yet in that theorem. We can just reach the kinetic time scale times L to the minus epsilon.
Yeah, but my question is, if you replace, say, that L to the minus epsilon with 1 over log L or something like that, there is any hope to get better? No, maybe not. I mean, I'm just
maybe yes, but really, as I said, the holy grail is to get to T equals T kinetic without a log loss, without an L to the minus epsilon loss, etc. So it might be that the L to the minus epsilon is a log loss. We did not really follow it. We did not really try to optimize what this L to the minus epsilon loss is. But what you the big problem is to get to T equals the kinetic time scale.
Thanks.
Okay? In terms of those scaling laws, you should think of them as sort of, if you forget about the epsilon for a minute. So this, for example, this scaling law, you're saying that alpha is like L to the minus 1, which means that you like alpha L to the order of 1 in the limit when L goes to infinity and alpha goes to 0. So this is sort of a similar scaling law, like the Boltzmann gradient. Okay, so the epsilon, the appearance of epsilon is because the theorem is, in a way, it's really, in a way, a subcritical theorem. It sort of does not reach the critical threshold, which corresponds to epsilon equals to 0.
Okay, thank you.
Okay. So what else do we want to say? What I would like to say is that this, essentially, the theorem is with up to those L to the epsilon losses, the theorem is sharp in the following sense. In what way? So as I said, that we cannot reach outside this blue region. In fact, outside this blue region, what we'll be showing is that the Feynman diagram expansion of the solution, we'll see that the proof is based on an expansion into Feynman diagrams. We show that this Feynman diagram expansion diverges absolutely in a certain sense outside the blue region. Okay, so if you want to extend this blue region all the way to this red line, then there needs to be some cancellation that is a major cancellation that is going on between the different Feynman diagrams. Okay, so around the same time that we published this work, there was a work of Charles Collot and Pierre Germain, and that covered part of the blue region. I believe this part, something like that. But this was an independent work. Okay. All right. So if there are no further questions, I will move on to discuss some ideas and what are some of the things that come into play with this theorem, with the proof of this theorem.
May I interrupt you, Zaher, with
Yeah.
a question also? So
Yeah.
about the oblique red line.
Yeah.
So is there, I know that this is the limiting line, as you said, the physically limiting line, but if we want to ask by curiosity, do we know something about the solution of your equation when you take t above this oblique red line?
Okay, so okay, so that's in some sense what you're asking is, do we know anything about the solution of NLS for times that are above this red line?
Yeah.
It depends who you're asking. I mean, from a mathematical, if you're asking me in terms of a mathematical result, there are absolutely no mathematical results that reach this time scale. Even the major problem for us in the proof, in a way, boils down to understanding the behavior of the solution of NLS, and this is really the limit of what we can do. Okay. In terms of, so yeah, if this was your question, that's my answer.
Okay, thank you.
Yeah, I mean, probably there are physical theories that sort of conjecture what's happening after this kinetic time scale. For example, in the linear setting, when you consider a linear Schrodinger equation with a random potential, there are some answers. You can, in some cases, go beyond this kinetic time scale. There's work of Salmhofer, Yao, and Erdos that sort of gets to regimes of timescales that are beyond this kinetic regime. So sort of a dissipative regime. It's not at all clear whether these things are relevant or they hold for a nonlinear equation. It's not at all clear there. Okay, but it's an interesting question to ask: what happens after this kinetic timescale? Okay, so at this kinetic timescale, you expect that the solution of NLS is sort of governed by the solution of the kinetic equation, and then you can ask, what about much longer timescales? That's an interesting question. I'm afraid I do not know what happens there. Okay, so let's talk about the components of the proof. So as I alluded to before, the proof can be divided into three main components. The first component is a Feynman diagram expansion of the solution of NLS. We'll talk a little bit about that. So basically, this is just expanding the solution in terms of its iterates up to a very high iterate. So you write your solution as the 0th iterate, which is essentially the initial data, then the first iterate up to the nth iterate, and we will organize those iterates in terms of something called Feynman diagrams. And then we, of course, afterwards, we have to account with the remainder. Okay, so doing this, writing the solution as such is not a big deal. This is something that was very well known. But what is new is to obtain sharp estimates for those iterates and also sharp estimates for the remainder. Okay, otherwise we do not have a rigorous proof. In order to get a rigorous proof, we need the sharp estimates for those, and we need sharp estimates for this remainder. Okay, each of those iterates, U sub n, is a 2n plus 1 linear in the initial data, and those will be organized in terms of Feynman diagrams. I'll talk a little bit about that on the next slide. So after you have this nice expression, and this is where the limitation on the time scale happens. This is what I was in answering the previous question when I said that the major part of the solution of this problem is understanding the solution of NLS up to as long of a time scale as you can. This is where the restriction comes from, in terms of sort of understanding in a way what is the time scale for which you can prove the convergence of this series of Feynman diagram expansion. It's sort of, you can think of it as a sort of power series expansion of the solution, and you want to see the radius of convergence of this power series expansion. And this radius convergence is something that is essentially dictated by the time scale for this expansion to converge. So after you have this expansion, you can start computing the expected value of U hat of k squared, and then you identify the leading order term versus error term. I won't do this computation here today, but the point is that once you isolate those leading order terms, then there comes a number theoretic argument, because the aim of this argument is to show that those leading terms can be approximated for L goes to infinity by the integral appearing in the wave kinetic equation. So you can see that this is something that you might expect, because the Fourier space for the nonlinear Schrodinger equation is a discrete space, whereas the solution of the wave kinetic equation is a continuum solution. Okay, so there is a passage from the discrete to the continuous, and such passages, once there is a parameter, they turn out to be a number theoretic problem is involved. Okay.
Zaher,
yeah.
I will interrupt you one more time, sorry. So just to remind you that your time is almost up, so you may have a few minutes maybe to conclude.
Okay, so I'll be very selective in terms of what to talk about. So how many minutes, just to be...
I think 2-3 minutes maybe. Just
2-3
to get
minutes. Okay. Okay. So okay. So I'll probably try to wrap up in a couple of minutes. So maybe I'll just talk a little bit about this step and those Feynman diagram expansions. So basically, the Feynman diagram expansion at 0th order is something that is very simple. So you write your equation in Duhamel formulation. This is the integral form. This is the initial data e to the it Laplace of the initial, and this already gives you the 0th order Feynman 0th order expansion of your solution. This is U0, and this is the remainder. And then in this remainder, so this is basically u bar u squared u. So in order to to get the first iterate, you replace all the u's by the initial data. So this would give you the this is over here u1. Okay. In order to see the expression in terms of diagrams, so you look at the Fourier transform of u of t. Actually, it turns out to be more convenient to look at the Fourier transform of e to the minus it Laplacian of t, so sometimes called the interaction representation picture at k. So you get this is u initial hat at k, and then over here you get minus I, you get the sum over k1 minus k2 plus k3 equals to k, the integral from 0 to t, e to the I omega t. You have u initial hat at k1, u initial hat at k2, bar u initial hat at k3, okay, ds, which you can integrate easily, this thing. So, but the point here is that we represent this by a dot. We represent this by a tree like such, where we put k over here, and you put k1, k2, and k3 over here. So whenever you have such a tree, we call this a decorated tree. You have that k is equal to k1 minus k2 plus k3. And then if you look at the second iterate, so for example, you replace this thing by, again, what the first iterate is, this u1, and which corresponds to having a branching node over here. And so I don't have much time to explain that, but in general, if you're talking about the nth order expansion, you get trees like those, and you get decorated trees like those, and those are things that are used to organize the iterates of the solution. So in other words, the nth iterate of the solution will be a sum over all trees, or all expressions j sub t associated with trees. And those trees have n branching nodes. Each branching node corresponds to then iteration of your equation. Okay, so and the problems are first to estimate these iterates, to get a good estimate on these iterates, and second, and more importantly, to get an estimate over the remainder. Okay, so maybe just 1 minute. I won't go about the estimates of the iterates, but in terms of the remainder, if you want to estimate the remainder, then you write the equation, you linearize the equation around those iterates, and you get the following equation for the remainder. There's a linear term, which is the most important term to bound, a quadratic term, and a cubic term, because you're starting from a cubic equation. And this linear term is essentially, in Fourier space, a large random matrix that gets multiplied by R. And the key point is to get a good estimate on this large random matrix. And here, so this large random matrix in Fourier space, you can call it M. The trick is to use a high order TT star approach. So TT star approach are very good in terms of capturing cancellations. Here you have a lot of cancellations that are coming from randomness or Gaussian cancellations. So what you do in order to capture all of that, you want to estimate the L2, basically the L2 to L2 norm of this large random matrix. What you do is that instead of estimating the L2 to L2 norm of this large random matrix, what you do is that you take very high powers of it. So you look at M star M, you raise it to a very high power D, and you estimate the L2 to L2 norm of this sort of much more complex matrix, and then you take a factor of 1/2D. This might seem like something that complicates your life a lot. In a way, it does, but it allows you to capture all the cancellation from the randomness that appears. Okay, so this is, but luckily enough, as I said, again, the estimation of this random matrices turns out to reduces to an estimation of like the trees, something. It turns out that estimating this random matrix is very similar to the estimating the trees that we had to do. And okay, so this is each one of those are trees if you linearize around T1 and T2, but okay, let's not go into that, and we'll finish here since we're out of time. Okay, thank you for your attention.
Thank you, Zaher. Thank you for the rich talk. So we have room maybe for one question.
Perhaps just a quick one. Then I'm going to say something that I'm completely not an expert about. So you say the series might diverge absolutely, right?
Yeah.
But to compare the sum of two series, you don't really need that they converge absolutely. Do you? I mean, there's something called Borel summation. So that's where I know just the buzzword, but I don't know what it is. But it's something which allows you to compare two series they are not absolutely convergent at all.
Oh, absolutely. So you're completely right. I agree with you. The Feynman series expansion diverges absolutely, and we proved that it diverges absolutely. But as you said, it might converge conditionally, and it might be there. But for that to happen, one needs to capture some sort of cancellation. It's not clear whether this cancellation holds or not. But
yeah.
But indeed, as you said, there must be some rearrangement of the terms that might allow you to retain some level of convergence, but it's not so clear.
But does the term Borel summation ring a bell with you, or?
Borel summation? It doesn't.
Okay, so
But
maybe I know nothing about it. Maybe you can Google it once and see what it does. I have no idea whether it could be useful or not.
Thank you. I'll look into it.
Okay, thank you, Nicolas Rochery. That was a question from Nicolas Rochery from Lyon. Because Zaher is not seeing, maybe.
Yeah, I'm not.
Yes, sorry. The only time I forgot to introduce myself was when it was actually useful.
No problem. So thanks again, Zaher, for the nice talk.